Hi, this is Dave. In this episode of Dr. Dave's Diversions, we'll be diving deeply into another version of BASIC, or BASIC-like language. In this case, the programming language used by this calculator, the Casio fx-4000P, my scientific calculator from the mid-'80s. This calculator came out in about 1985. If you follow David on the 8-bit guy, he just last week did a nice video about handheld computers from the 80s. And I didn't have one of those, but I did have this Casio calculator. And one of the interesting things that David said is he would hesitate to have brought his handheld computer to school because nerds were harassed by other students or it might get damaged or something. Well, I took this to school all the time. And in fact, that's exactly why I have this specific model. The interesting thing about the Casio FX4000P is it came out simultaneously with the famous Casio FX7000G, the first graphic calculator ever. But I didn't want that one. The reason I didn't want that one is when the 7000G came out, they became banned from being used in the class. They were too powerful, the graph functions. It was basically considered cheating. So having the 4000P, which is programmed exactly the same as the 7000G, but just has a one-line dot matrix display instead of that much larger display where you can display graphs, it has a lot of the same functions, and actually from a programming perspective is a little more powerful. It has more programming steps or more memory for programs than the 7000G. That's why I chose this calculator. And when my teachers in high school or my professors in college went up and down the aisles to see what calculator you were using, if they saw this, they said that was fine. If they saw that big graphing screen, you weren't allowed to use it. So this was a nice calculator to have then, specifically because it was allowed to be used in coursework. And what we'll do in the episode is do some archaeology and explore another ancient system. In this case, the original BASIC from Dartmouth College, circa 1964, running on the Dartmouth Time Sharing System. The authors of the BASIC programming language are John Kemeny and Tom Kurtz. And John Kemeny, who was in charge of mathematics at Dartmouth at the time, he's a big name. John Kemeny has some pedigree. He was at Los Alamos when they were developing the A-bomb, and he reported to Richard Feynman. He later in grad school was Albert Einstein's assistant in school. And Tom Kurtz is a professor that he hired later at Dartmouth. And together they developed or have BASIC attributed to them in circa 1964. Now, what I happened to discover, and this is sort of a review of it, is there's a really neat documentary called The Birth of BASIC that Dartmouth produced on the 50th anniversary of that birth of BASIC. And you can watch it on YouTube. I'll have links in the comments. It's about a 40-minute long documentary. But one of the neat things they captured in the documentary was this student actually programming BASIC on the DTSS system in Dartmouth BASIC on the teletype. And the camera zooms in close enough that we can actually read every line of that program. So what I propose we do today is let's take that program that student had written in Dartmouth back then and convert it to run on the Casio calculator to show how that student in their freshman mathematics class, how 20 years later I would have done that when I was in college in the 80s using this device instead. Now, one thing that's neat about this project at Dartmouth, the DTSS system, is it was all bankrolled by the federal government, the National Science Foundation. Well, Kemeny and Kurtz were the recipient of a grant for hundreds of thousands of dollars that caused them to develop BASIC and the DTSS system. Because the NSF is a federal agency, all those documents about that project, even back then, like for instance the final report from 1967, is available, and here's the cover page to it. Not only that, I was able to find the typewritten assignment that student was fulfilling by writing that program on that on the teletype, and that's the assignments right here. So we have all the documentation we need. Let's go see how that student's program worked. Get it running first on a machine that has BASIC, like the Commodore 64 here, and then we'll move on and port it to the calculator. So here we are at my Commodore 64, and I've typed in the program that Dartmouth student had written that we read off the paper terminal and saved it to a floppy disk. So let's load that. All right, so let's see if their program worked. So the result it's saying is it's saying that when x is approximately 0, y is -1. Well, what this program is trying to do is trying to find the root of the function, which is the point at which the function crosses the x-axis, or also called the x-intercept. And so this is saying that that when x is 0, y is -1. Well, that's not the point where it crosses the x. It's because it's down at -1. We want it to be near 0 for the y. So let's go see what's wrong with this program. So we can see here that the student set up the problem description, and they call the function f of x and say if it's greater than 0, then go to 100. Well, from my looking at this and reading the problem again, what they've done is they've reversed the test here. This should be greater than. So we'll make that change and go down here and run the program again. And now the answer is saying in line 260 there, it prints x and then the function f of x, which is the y coordinate. So here it's saying that x is 0.733156681 on the x-axis, when at the y-axis we're at -8 times 10 to the -7th, so nearly 0. So that is an approximate x-intercept. It's basically saying we're intercepting the x-axis at the value 0.733. So let's see if that's correct. So to do that, we'll go to running Wolfram Alpha. So here we are at wolframalpha.com, and this is a modern, graphing calculator, like a scientific calculator. So let's give it that function from the 60s era quintic or quint problem from mathematics at Dartmouth University. And what we're going to do is we're going to ask it to show us the x-intercept or determine the x-intercept for that quintic function. And here's the Wolfram Alpha result. It says x is 0.733157, so a rounded version of exactly what the Commodore 64 said when we ran that student's program once we fixed the bug. And it also plots the function right there, and we can see that's what that particular quintic function looks like. And that where that red dot is, that's the root or the x-intercept that we calculated. So so now we've got the program working. Let's use that program with the fx-4000P, a non-graphing calculator, to solve this graphing problem, or this one problem that could be addressed using graphing, using the fx-4000P in its basic-like language, by starting with that student's program. All right, so let's have some fun looking at what the Casio programming is like and port that basic program to the Casio fx-4000P. So the way I've decided to do this, because it's very difficult to look at the programming language on the calculator itself with just that one line, and we'd be scrolling back and only seeing a small window of it, I'm going to use a variant of the syntax by writing the statements on individual lines instead of just one long line. And I'm going to call this language a pseudo Casio, or PCAS, and then use and create files with PCAS extension that have specifically those characteristics. So in this pseudo Casio language, here's the way that I've written that particular quintic function solving program. The main program is in quintic.pcas, and the function defined in that basic program is in quintic eqn.pcas. So let's start off by looking at the latter of the two. And this is a simple program in that language. So when I said I wrote this pseudo language, I'm basically saying, here's the way, we know from experience that this is the way you might have written it in BASIC. Well, I just wrote a small conversion tool that can turn something of that form into the Casio form that you would type into the calculator. So let's look at this notion of this pseudo Casio into Casio first. So here we have an equation that should look familiar to you. For instance, that's exactly the way you could write it on the Commodore 64. And the Casio has just a subtle difference in the syntax. In this case, instead of the hat, or in the 64's case, the up arrow, it uses this operator x to y. So all the conversion does is convert between those two. So by putting this in a program in the Casio, all I have to do is set x to a particular value and run that program, and it would produce the result. So looking at the two programs here, in set, I'll occasionally show you the basic version that we typed in from the Dartmouth students' work. Let's compare them to each other. So first, in the basic program on line 10, we defined the function f of x exactly as written in the quintic equation right here. So that is the equivalent of line 10 in the basic program. That particular function becomes a subroutine on the Casio, which supports subroutines, but it supports them by having you write them as a separate program. So we'll write one program and put it into the Casio as just this one line right there. Now continuing on, the next thing we do in the basic program is on line 20, we read n from the data, and the data is defined in line 900 in that basic program. So on the Casio, there isn't the read in data feature of BASIC. Instead, you can just explicitly put the value right into the variable by an immediate assignment, or we can read it from the user. So let's do the latter. So here in the code in quintic.pcas here, the first line I'm saying, basically prompting the user to enter the value of n instead of us reading it from the data portion of the basic program. And this question mark operator is like input in BASIC. And the arrow operator is the assignment. So we're saying, ask the user for a value and assign that into the variable n. So this is the equivalent of line 20 in the basic program. The next thing we do in the basic program is we do 3 assignments where it says let variable equals value. In this Casio programming language, the way that's done, again with the arrow operator, is you take it just reverses the two things around, the variable and the value. So we say put the value into this variable. So that's exactly the equivalent of lines 30 through 50 in the basic program. Next, we have a for loop on line 60 that says for I equals 1 to n. Now, how do we implement that in Casio? Let's take a look at that. So starting here and finishing right here, that is the equivalent of the for loop that you see in the basic program beginning on line 60 and ending on line 200 where it says next I. So that loop. So what the Casio calculator in this language has is, instead of the basic syntax, it has things that have the same semantics. So just like the assignment was a equals 0 in BASIC, it's 0 arrow a in this Casio programming language. The semantics is exactly the same. Assign this value into this variable, but the syntax is different. So in this case for the loop, what we have to do is in the for loop essentially starting in line 60 says, we'll first set the variable I to 1, and then every time around the loop increment until you get to n. Well, if we look at the Casio program here, we do first set I to a value, but I decided to count down instead. You could do it either way, but I decided to count down. So I set it to 20, and I'm going to count down until it's 0. And then in a for loop, you have an action when you get down to that next that jumps back to a previous place. Well, in the Casio language, you have 2 things that can do that. The goto is the only control structure that will cause it to do the loop. So we have to implement the for loop with the goto. But the Casio language has a label capability where you can label any statement with a numbered label. So that's what we're doing here. So we're saying at the top of the loop, that's going to be called label 1. So when we say go to 1, that goes to the top of the loop. That's the for loop portion of it. And then the third thing the for loop does is it tests, of course, to see when it should terminate going around the loop. When it, in the case of line 60, it says when it reaches n. Because we reversed it and we're counting down in the Casio program, we're going to test when it gets to 0. And that's what this is right here. The DSZ is a statement or a command in the Casio language. It says decrement the variable I mention and skip the next line if it's 0. So decrement, skip if 0. And it also has an increment skip if 0, so it could have been written that way as well. So decrement skip if 0 says when I finally gets down to 0, it will skip the next line, which is the goto, causing it to exit the loop, because we won't do the goto, and we'll arrive at this line here, which is the equivalent of saying display x, which is the equivalent to line 260 that says print x. Now, if we look at the pseudocode I have there, it says X, and then I drew this sort of little right triangle with a slash and a vertical bar. That's my own syntax. What that'll turn into is this little filled in right triangle in the programming language. So here's the significant difference between the two languages. In BASIC, you explicitly say print something. In the Casio language, instead of having a print command, what they decided to do was introduce a new separator between the statements. The statements are typically separated. In this case, in my pseudocode, I separated them by new lines, but in the real program language, they're separated by colons. Alternately, if you separate the two statements by this little right triangle, it means to display the result following the previous statement. So every statement can be separated with something that says to display the value. So that's how we do a print, and that's what causes X to be printed here. The other thing in line 260 of the program, it says print fnfx, so run the function on x. And so here I say, well, let's say f of x, and then call program 2, which is where we're going to store this quintic EQN program down here. So that's what causes it to print the y value, or the function of x, by calling the program. And then in the Casio language, I don't have to say display after that, because the result will implicitly be displayed at the end of the program. So that's basically how we're almost line for line rewriting that basic program into the Casio programming language. Now, what is that going to look like on the calculator itself? We'll go to the calculator in a second, but given those two programs, I wrote something that can turn them automatically into the equivalent Casio format. So quintic.pcas up here in my own, imaginary programming language, inspired by the way by what I see people do online when they're in the calculator community and they're talking about all this nerd stuff about how to write in the Casio language. They'll write it out in these separate lines instead of in the format exactly as you type it in the calculator, because it's more convenient and it's easier to read and understand the logic that way. But that quintic.pcas turns into this program right here, which is just a line-for-line translation of those, putting the right separators in between the lines, taking out unnecessary white space, and that becomes the compact program that we were going to type in, or that I already did type into the Casio calculator. Similarly, this one-line expression, or this function that we wrote here that we said we're going to store in program 2, that just turns into that there. So now we're all set, and we're ready to go to the calculator and run it there. So we have the quintic equation itself in program number 2, and then we have quintic.cas itself in program 3. So we're going to, now we're in run mode, so we can say program 3, execute. It asks us for n, just like it was reading from data in the basic version. And we can say n is 20, so that's the number of iterations. We run it. And there we have it. The same answer that we got on the Commodore 64. And a Wolfram Alpha gave us 0.733157, if I recall correctly. So we managed to run the function there. And what we did, and what we've managed to do, is use a programmable calculator from the mid-'80s, like a graphing calculator, where we didn't need the graph function because we did this sort of binary search in a number space, and kind of brute forced it and tested out where can we find where it crosses that, where the x-intercept is. So we did it. We got that program working on the Casio fx-4000P. As you can see, it's slower than the Commodore 64. I don't know how it compares to the GE system they were using back in the mid-'60s, but pretty neat that you can solve a problem like that on this calculator. Now the question was, I said I'm looking into variants of BASIC. Was that BASIC that we're using on there? Well, Casio didn't call it BASIC. In fact, Casio had their own BASIC that they used on their handheld personal computers. So I think it's fair to say it either way. I think it's not exactly BASIC, but what I was able to show you by looking at that sort of pseudo Casio code that looks almost more like assembler is what we can see is that the Casio programming language has features that would allow you to build BASIC. It has the control structures, it has conditional branching, it's got indirect addressing in the form of arrays. We didn't happen to show that, but these are advanced concepts. At the same time, it's got some very limiting things, like it can only use a certain number of variables, it can't do recursive functions very well because it doesn't have the ability to pass parameters to those functions. So I would say it's not BASIC, but it's a variant of it. So that's what I have for you this time. If you like this kind of content, whether it's the archaeology, working with the old computers, or the old programming languages, give me either a thumbs up or subscribe, leave a comment, tell me what you like or don't like about it. If you have a similar story about how you used a programmable calculator back then for doing programming, share it with us. And I'll see you next time.